Today, I want to talk about the ROM. ROM stands for Read-Only Memory. And last time, we discussed the RAM, or the Random Access Memory. Now, if you turn off power to the RAM, it loses data. However, if you turn off power to the ROM, the data is remembered. When you turn the power back on, the data is there. Now, if we make an analogy with the memory of a human being, the RAM stores information like what's on TV tonight. It's something that I'll probably forget in a day or two. But the ROM information is something that you're sort of born with. It's a program that comes with your existence. For example, if you're afraid of heights, that's something that's would be stored in a ROM memory. Or a little child is afraid of the under the bed monster at night. So at night he has to look under the bed to make sure the monster is not there. Well, that's ROM programming. That probably prevents you from going into dark caves and being eaten by a bear. So let's consider the structure of a typical read-only memory. Here I've sketched out a very simple ROM, or read-only memory. And there are many different ways to do a ROM. This is just one way it might be done. And if you understand one way a ROM is done, you can probably understand all the other different ways that the ROM can be done. So the white part here shows the memory part. It shows transistors in this particular ROM that are created during fabrication. So this ROM data cannot really be changed. So you better make sure it's correct, because it's going to be fabricated this way and you cannot change it unless you retool all of your masking and refabricate it, which you don't want to do. So you have to be careful with the information in a ROM, because probably it will only be written once or a few times, or in some different ROMs perhaps it can be written many times. So this particular ROM has 4 word lines. It has WL0, 1, 2, and 3. Now, there are 4 bit lines also. There's bit line 0, bit line 1, bit line 2, and bit line 3. And up at the top, shown in green, is a pre-charged circuit. And I have a decoder that's shown in yellow. And I have a sense amplifying circuits that sense the data on the bit lines that's shown at the bottom and in red. So let's give you an overview of how this ROM works. Now I have 2 address bits. I have address 0 and I have address 1. And 2 bits allows me to select the 4 different word lines. So when the word line is selected, the output of the selected NOR gate will go to a logic 1. And if a transistor is present, that transistor is represented as a 1 data. If the transistor is absent, that's represented as a 0 data. So if we take, for example, let's take word line 3 up at the top. So this data would be a 1. Since the transistor is absent here, this bit line would contain a 0, this bit line would have a 1, and this bit line would have a 1. How this circuit works is that every time the address changes, the A0 or the A1 changes, I want to generate a pre-charge pulse that will momentarily go to a 1 level and then return to a 0 level. And that pre-charge pulse disables all of my NOR gates. It forces all of the word lines to a 0. And this pre-charged pulse charges up all the bit lines to a 1, and the inverter at the bottom, shown in red, converts all the outputs to zeros. And so after a certain period of time, this pre-charged pulse will go away, and my decoder will be enabled to enable just one word line. Only one word line gets selected. So if I select word line 3, I output, let me change colors, I output 1, 0, a 1, and a 1. So let's consider the ROM timing. So this is very similar to the RAM timing that we presented in an earlier video. At the top here, I've shown my address waveform. And I've shown below that the pre-charge pulse. So whenever the address changes, I generate a pre-charge pulse. And that charges all the bit lines up to a 1 and disables my decoder. So since all the arrays, all the bit lines are at 1, the data output is at a 0 level on all the 4 data out bits. Now, when my pre-charge goes to a 0 level, my decoder is enabled, and if I have a transistor present, the output will go to a logic 1. If a transistor is not present, the output will just stay at a logic 0 level. Now, the key timing parameters for the ROM is the access time. So when I change my address, for example, right here I change my address, and I have to wait a certain amount of time for my data at the output to become valid. So a very fast ROM, it may become valid here. For a slower ROM, it may become valid here. So the access time is a time I must wait for the data to become valid. The cycle time shown here tells me how quickly I can change the address. Here is another way to make the ROM. This is a diode ROM, and the storage element is a diode and a fuse element. And how this ROM works is, if I want to write a 0 into the ROM, I have to raise, for example, this bit line high and this corresponding word line low, and run a large current in this diode and blow the fuse link. So if the fuse link is intact, I'm going to call that a logic 1. If the fuse link is blown, I'm going to call that a logic 0. Now here I've used a NAND gate decoder instead of a NOR gate decoder, since I want this selected word line to be at a logic 0 and all of the other word lines to be set at 1. So if this line is selected to a logic 0, the bit line 0 will be discharged through this path, and I'll have a 0 here, and the inverter at the output will convert that to a 1. Now here my fuse is blown, so the bit line will be pulled high through this resistor, and I'll have a 0 at the D1 output. Here is another type of memory called a flash memory. Here I've drawn the NMOS transistor as a basic ROM storage element, similar to what we discussed in the original ROM example. Now this transistor will have a threshold that we'll call VT1. Now I can do something very special with this transistor during fabrication, I can add a floating gate into this transistor. And what I can then do is I can apply a very high voltage, perhaps 12 volts at the gate, and run a large drain current in this transistor, and I can induce electrons onto this floating gate. Now this floating gate is surrounded by an insulating material. It's surrounded by an oxide, and it can store this electron charge for decades. And when I induce electrons onto this floating gate, I increase the threshold of this transistor up to V threshold 2. And I can call this transistor with the gate programmed with electrons, I can call that a logic 0. And if the electrons are not present on this floating gate, I can call that a logic 1. Now this program, or this flash memory, can be programmed many times. If I want to remove the electrons from this gate, I can set this gate voltage at a negative voltage, perhaps minus 9 volts, and I can raise this source line up to a high voltage, perhaps plus 6 volts, and I can remove the electron charge from the gate and transfer it over to the source region. And then the transistor is in a logic 1 state. So this transistor, this flash memory element, can be programmed many times, and under normal conditions the charge on the gate can remain for decades. Let me just mention one more thing here. If I want to do a read operation, this source line will be connected at ground, and I'll raise the word line voltage, and I'll raise it less than the VT2. And so in that situation, if the threshold is at VT2 or 0 is programmed, the transistor is like it's not there. It doesn't conduct any current. But if the VT1 exists in the transistor, and I don't have charge on the gate, then when I raise the word line up, I get current flow and I discharge the bit line.